The aims of this experiment are tracking the motion of the bottom of a falling slinky, comparing the measured position of the bottom of the slinky with the results from a computational model, and determining whether the motion of a falling slinky can be predicted with reasonable accuracy using computational methods. The principles and models involved in this experiment are Newton's laws of motion, including the momentum principle and the position and velocity update formulas, as well as the force of gravity near the surface of the Earth, the drag force, and the average speed for non-constant forces. There were parallels between the computational model and the measured data plot. Although they did not match exactly, they were reasonably similar. Thus, it was shown that the fall of the bottom of a slinky can be modeled with reasonable accuracy if the proportionality constant for the drag force is chosen appropriately. On its initial state, the slinky is stretched. There are two main forces acting on the bottom of the slinky: the force of gravity due to the Earth, which tends to make the slinky stretch, and the spring tension force, which tends to pull the bottom towards the center of mass. It's a restoring force. In equilibrium position, the force of gravity equals the restoring force. When not in equilibrium, the resultant force causes acceleration and tends to make the bottom of the slinky fall. When the top of the slinky is released, the slinky is expected to fall to the ground as the force of gravity takes over. When this occurs, as the velocity of the bottom of the slinky is non-zero, the force of drag will also act opposite to the slinky's fall motion. In this experiment, the system is the slinky, whereas the surroundings are the Earth and the air. On tracker, the origin is set on the ground. Also, knowing that the height of the person to the left of the slinky is roughly 1.75 meters, the scale is set up using a calibration stick. On the model, the system mass and the initial conditions of the bottom of the slinky are set up. The constants for the magnitude of acceleration due to gravity near the surface of the Earth, as well as the vector, the unit vector j hat, and the proportionality constant for the magnitude of the drag force are set up. On the code, the net force is the resulting force from adding the force of gravity and the tension of the spring force due to the slinky being stretched. The position is updated using the velocity and position update formulas, using the net force as the final force for each time step. The program advances to the next time step. The code is the same for when the slinky is falling, but in this case the tension force is neglected, and instead the only force opposing the motion of the slinky is the drag force. The following plots are obtained. The plot to the left is generated with a computer model, whereas the plot on the right is generated with tracker. When plotting both datasets on the same graphs, it can be seen that both the predicted and measured motions follow similar trends. The bottom of the slinky remains stationary at first, and then the bottom starts falling with some acceleration, although the predicted model shows a lower acceleration than the measured model. Some sources of error include that the model only considers motion in one dimension, while the slinky moves in two dimensions in real life. Also, the drag proportionality constant affects how close the computational model approaches the measured data plot. Other interactions, such as the collision of the collapsing slinky with its bottom, are not considered in the model, and the net force could be different when the slinky starts dropping. Why does the bottom remain stationary? When the top of the slinky is released, the coils collapse downwards progressively. A mechanical wave, specifically a compression wave, is generated. The tension acting at the bottom of the slinky remains equal to the force of gravity until the perturbance gets to it. In conclusion, the motion of the bottom of a falling slinky was tracked and a computational model was developed to predict this motion. When plotting both datasets on the same graph, it was observed that the motion can be modeled computationally with reasonable accuracy as long as the proportionality constant of the force acting against the motion is appropriate. The effect of the bottom staying momentarily at rest is attributed to the fact that the net force does not change until the compression wave does not reach it.